Hello everyone, my name is Aya Salama and this is Lab 4 of Physics 2212 bar magnets. First, for the introduction. Purpose. The purpose is to observe a better understanding of magnetic fields through a visual representation, to visually observe the relationship between distance and the magnetic field, and to use the distance dependence of magnetic fields and the Bouvet-Savart law to find the magnetic moment of a bar magnet. So then our system is obviously the bar magnet. Surrounding is everything else. The results we gained from this experiment was negative 2.8049, and the magnetic dipole moment we got from this experiment was 3.69. Now here are the fundamental principles related to this lab. First, let's start with the Bouvet-Savart law. This law relates the magnetic field at a point to a tiny current element. Then we have the magnetic field of a dipole. So a magnetic dipole is a closed circulation of an electric system. And lastly, a fundamental principle is the distance dependence formula. The magnitude of the magnetic field due to a bar magnet falls off with distance. So the absolute value of the magnetic field of the bar is going to be KRN, and then that whole magnetic field of the dipole, that formula, and then the dipole of the axis is going to be that formula. Now for the experiment's procedure. First, we oriented the phone to make the magnetometer orthogonal to the Earth's magnetic field. Then we found the location of the magnetometer chip on the phone. We measured distance between the magnetometer and the bar magnet for on and off axis. Initial conditions: bar magnet and magnetometer on the phone. Details: first, the location of the magnetometer on the phone was pinpointed by sliding the phone perpendicularly to the ruler with the bar magnet on one end of the ruler in order to see which position of the phone relative to the magnet was the strongest field being read. Here are our observations of the experiment. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The position of the magnetometer gas has no effect on the measured x component of the magnetic field. As the magnetometer moves closer to the magnet, the measured x component of the magnet field increases. Here's a look at the experimental data for this lab. You can see the linearized data of the graph plotted on the right by taking the averages of all the measurements we've taken for the experiment. This was our procedure for calculating N. We used the first formula, magnetic field equals Kr to N, took the lateral log of both sides, and then found N by isolating the variable. After we found N, we could use that number to calculate U mag. Using this whole formula over there shown, we found U mag to be 3.69. So now for the code of this experiment. So we refined U mag as 3.69, which is the magnitude of the magnetic dipole moment. And then we defined a function called dipole D, which gives you the magnetic field given the magnetic dipole moment and also R, and then I scaled the areas to make it fit and find the distance as 0.25. And then I went ahead and set the observation locations of the different points on the axis and the perpendicular. Now I'll just be showing you the rest of the code where we find the magnetic field of all of these points on the axis and perpendicular, and then make arrows representing the magnetic field at those points. Now we found D given D perp from my experimental data, and then we found the magnetic field at a point 45 degrees from the axis. Now after we run all that code, this is the output. So the magnetic field on the axis is in orange, the magnetic field perpendicular to the axis is in blue, and then lastly the magnetic field 45 degrees from the axis is in purple. As you can see, the magnetic field on the axis points to the right, or the positive x hat direction, and the magnetic field perpendicular to the axis points to the left, or in the negative y hat direction. Some assumptions and potential errors. So the bar magnet acts as a magnetic dipole. Magnetic field falls off a distance as distance increases. other electronic or magnetic objects skewed the magnetometer data, and the exact location was not found precisely. What if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some magnetic field? How would the results change? Answering that, the Earth's magnetic field would interfere with the bar magnet's magnetic field, thus skewing the results. And then for the second question, the answer would be the magnetic field magnitude would double, but the direction would stay the same. Thank you guys so much for listening.